Inductive voltage surges occur when you try to instantaneously change the current in an inductor.
The problem is usually associated with long electrical power lines that are providing a lot of current. Let's start out by using a lumped parameters model of a power line and see where that leads us. My model will lump all of the inductance in the power line into a single equivalent inductance L. The line is supplying power to a load, and there's a switch here that can turn power off to the load. Got a generator at this end of the line providing a voltage V sub G. I want to find out what happens to the voltage V sub S just to the left of this switch after it opens up. The underlying assumption in this model of the transmission line as a single inductor is that the entire power line shares the same current, which I'll call I. So when I open this switch, I stop the current everywhere in this line simultaneously. This is going to cause problems since an inductor stores energy as current and it's not possible to change energy instantaneously. The equation governing this circuit is V sub G minus V sub S is equal to the inductance L times the derivative of the current with respect to time. di by dt is the rate of change of the inductor current. So when I open the switch, the current changes instantly at the switch, and since this is a lumped parameters model, that means that the current everywhere in the line also changes at that same instant. So if I plot the current as a function of time, it goes from a positive number instantly to 0 and stays there. The rate of change of the current here is negative infinity. Plugging negative infinity into this equation tells me that V sub S must go to positive infinity. That's not a useful number for an engineer. We can't design anything that can withstand an infinite voltage. So if, for example, a circuit breaker suddenly cuts off currents to the house, you get an infinite voltage and something shorts. So in this case, where the entire power line is modeled by a single inductance, we don't get a useful result, which isn't so great for an engineer. Since that didn't work out, let's try a distributed parameters model. In this model, the current and voltage are functions of distance along the line, and the current isn't the same everywhere. With a distributed parameters model, I'll draw my circuit like this. There's still a long transmission line connected to the load through a switch. I still want to find out what happens to the voltage V sub S when I suddenly open this switch, and I still have an applied voltage V sub G at this end of the line. The current in the line is still I just before the switch opens. In the distributed parameters model, the line is now represented by a distributed parameter called the characteristic impedance, which is represented as Z0. Now when I open this switch, the current here can stop, so I get 0 amps, but the current in the rest of the line doesn't respond instantaneously. In this model, it takes time for the information that the switch is open to propagate up the line and stop the current everywhere. In this model, the voltage surge caused by the switch opening is I times the characteristic impedance Z0. Z0 is usually a fairly large number, so this can be a large voltage, especially if the current's high. However, it's still a useful number. I can design a circuit to withstand a high voltage, but I can't build anything that withstands an infinite voltage.